Welcome! In this session, we'll tackle the problem number 1233, remove subfolders from the file system. This problem challenges us to efficiently process a list of folder paths, identifying and removing subfolders while retaining only the top-level directories. Let's dive into the details. In this problem, you are tasked with managing a list of folder paths in a file system. Each path in the folder list represents a directory, and these paths are structured using forward slashes, such as /A or /A/B. The goal is to identify and remove any folder paths that are redundant. A folder is considered redundant if it is a subfolder of another folder in the list. For instance, if you have /A and /A/B, the folder /A/B is a subfolder of /A, and therefore it should be removed. After removing all redundant folders, you need to return the remaining folder paths in any order. The problem specifies that the input will be a list of strings, and the output should also be a list of strings containing only the top-level folders that are not redundant. Let's understand this with the first example. The input folder list is /A//B, /C/D, /C/D/E, /C/F. Here, /A//B is a subfolder of /A, so we remove /A//B. Similarly, /C/D/E is a subfolder of /C/D, so we remove /C/D/E as well. The remaining folders /I, /C/D, and /C/F are not subfolders of any other folder in the list. Thus, the output is /A//C/D, /C/F. This demonstrates how we systematically eliminate redundant folder paths to leave only the top-level directories. Now, consider the second example. The input is /A//B/C, /A//B/D. In this case, both /A//B/C and /A//B/D are subfolders of /A, so they are removed. The only folder remaining is /A, which is not redundant because it has no parent folder in the list. The output here is /A. This illustrates how the problem prioritizes top-level folders by removing all their nested subfolders. In the third example, the input is /A//B/C, /A//B/CA, /A//B/D. Here, none of the folders are subfolders of one another. For instance, /A//B/C is distinct from /A//B/CA and /A//B/D, and they do not share a direct parent-child relationship. As a result, all the folders remain in the output. This highlights a scenario where no redundancy exists, so the output matches the input /A//B/C, /A//B/CA, /A//B/D. This shows that the solution must carefully distinguish between nested paths and paths that only share similar prefixes. Finally, let's look at some constraints and edge cases. The number of folder paths in the input list can go up to 40,000, and each folder path can have a maximum length of 100 characters. The paths only contain lowercase letters, digits, slashes, and dots, and every path starts with a forward slash. Edge cases include scenarios where all folders are subfolders of a single parent folder, such as /A//B, /A//B/C, /A//B/C/D, where only /A remains. Another case is when no folders are subfolders of one another, like /A//B/C, where all folders remain. Highly nested paths, such as /A//B, /A//B/C, /AC/D, /AC/E, should result in only the top-level folder /I. Lastly, folders with similar prefixes but no nesting, like /A//B, /A//BC, /A//B/D, should all remain, since they are distinct paths. These constraints and cases ensure the solution handles a wide range of inputs efficiently and accurately. To begin with, let's consider the brute force approach to solving this problem. The intuition here is fairly straightforward. We compare each folder path with every other folder path to determine whether one is a subfolder of the other. We do this by checking if the folder path starts with the other path and if it's followed by a trailing slash. If we find that a folder is a subfolder of another, we exclude it from the result. The steps involve iterating through all folder pairs, removing subfolders, and returning the remaining set of folders. However, when we analyze this approach, we see that it comes with a significant computational cost. The time complexity is O(n²*k), where n represents the number of folder paths, and k is the average length of the paths. The space complexity is O(n) to store the results. While the brute force method is simple to understand, the nested comparisons make it inefficient, especially for large inputs. This trade-off between simplicity and performance highlights why this method might not be practical in real-world scenarios with substantial datasets. To improve upon the brute force method, we can use an optimized approach that leverages sorting. By sorting the folder paths lexicographically, we ensure that all subfolders of a folder appear immediately after the folder in the sorted order. This eliminates the need for nested comparisons. The process involves first sorting the folder paths, then iterating through the sorted list. We maintain a result list and, for each folder, check if it starts with the last folder in the result followed by a trailing slash. If it doesn't, we add it to the result. The key insight here is that sorting groups subfolders with their parent, simplifying the identification of subfolder relationships. This approach not only streamlines the process but also helps us avoid redundant checks, making it far more efficient. The aha moment lies in recognizing how sorting can transform a seemingly complex task into a straightforward linear pass. Examining the complexity of the optimized approach, we find that sorting introduces a pre-processing step with a time complexity of O, n * k * log n, where n is the number of folder paths and k is the average length of the paths. After sorting, the single pass through the folders adds an additional O, n * k, for string comparisons, making the overall time complexity dominated by the sorting step. The space complexity remains O, n, as we only need to store the result list. When we compare this to the brute force approach, the optimized method is significantly more efficient. It avoids the O, n * k nested comparisons entirely, reducing the problem to sorting followed by a single pass. However, sorting does add some overhead for smaller inputs, which could be considered a minor trade-off. Despite this, the gains in scalability and reduced computational cost make this approach highly suitable for larger datasets. The chosen strategy for this problem is the optimized sort and check prefix approach. It strikes a balance between efficiency and simplicity, leveraging sorting to minimize unnecessary comparisons. By grouping subfolders with their parent folders in the sorted order, we simplify the task of determining subfolder relationships. The brute force method, while intuitive, is computationally prohibitive for large inputs, making it less practical. On the other hand, the optimized approach reduces the time complexity from O, n * k, to O, n * k * log n, offering significant performance improvements. Alternative methods, like using tree structures, could achieve similar results but would introduce additional complexity and higher space usage, making them less attractive. The sorted approach stands out as the most balanced solution, delivering both performance and ease of implementation without sacrificing correctness. This makes it the ideal choice for solving the problem effectively. The goal of this problem is to remove subfolders from a list of folder paths. A folder is classified as a subfolder if its path is a prefix of another folder path, and the next character in the longer path is a /. For instance, given the input list /a//b /c/d /c/d/e /c/f, the output should be /a//c/d /c/f, since /a//b and /c/d/e are subfolders of /a and /c/d, respectively. To solve this, the first step is to sort the input list lexicographically. Sorting arranges parent folders and their subfolders together, making it easier to group them. For example, sorting /a//b/c/c/d results in /a//b/c/c/d. This sorting step has a complexity of O, n * log n, where n is the number of folder paths. After sorting, we initialize an empty result list, which will store our final answer containing only the non-subfolder paths. This result list is key to keeping track of the valid folders as we process the sorted input. Once the input is sorted, the next step is to iterate through the list to identify and filter out subfolders. The approach here is straightforward. For each folder in the sorted list, first check if the result list is empty. If it is, simply add the folder to the result list. Otherwise, compare the current folder with the last folder added to the result list, which we'll call the parent folder. To determine if the current folder is a subfolder of the parent, we verify two conditions: first, that the current folder starts with the parent folder using the starts with method, and second, that the character immediately following the parent folder in the path is /. If both conditions hold true, it means the current folder is a subfolder and should be skipped. If not, the folder is added to the result list. This comparison process is efficient, as the subfolder check is performed in constant time for each folder. Once all folders are processed, the result list contains only the non-subfolder paths and is ready to be returned. This algorithm leverages several key insights to achieve its efficiency. First, sorting the folder paths simplifies the problem significantly. By sorting the paths lexicographically, parent folders always appear before their subfolders, enabling us to identify subfolder relationships with a single pass through the list. Second, the subfolder check is both accurate and efficient. By using the starts with method along with the / condition, we avoid misclassifying folders with similar prefixes, such as /abc and /abcd, as parent and child. Third, the algorithm employs early pruning. As soon as a folder is identified as a subfolder, it is skipped, eliminating unnecessary comparisons and keeping the iteration fast. In terms of data structures, the input is stored as a list of strings, and sorting is performed in place to minimize memory usage. The result list, which holds the final output, provides O(1) insertion time, ensuring that the solution remains both time and space efficient. When applying this algorithm, it's important to consider edge cases that may arise. For instance, if the input contains only a single folder, such as /a, the algorithm directly returns that folder. Similarly, if there are no subfolder relationships in the input, the output will simply mirror the input. In cases of deep nesting, like /a//b, /a/b/c/d/e, only the highest level folder, /a, is retained. Another critical scenario involves folders with similar prefixes but no parent-child relationship, such as /abc and /abcd, both of which should be retained in the output. In terms of complexity, the algorithm is efficient. Sorting the paths takes O(n*log n), while the single pass through the list for comparison operates in O(n), resulting in an overall time complexity of O(n*log n). The space complexity is also optimized, with O(log n) for in-place sorting and O(k) for the result list, where k is the number of non-subfolder paths, leading to an overall space complexity of O(n). This Python implementation solves LeetCode problem number 1233, remove subfolders from the file system, using a straightforward and efficient approach. Here's a step-by-step breakdown of the solution. 1. Sorting the input list. The first step is to sort the folder paths lexicographically, alphabetically. This ensures that parent folders appear before their subfolders in the sorted order. For example, /a//b, /c/d, /c/d/e, /c/f remains sorted in the same order. Sorting is crucial for efficiently identifying subfolders later. 2. Initializing the result. After sorting, we initialize the result list with the first folder from the sorted list. This folder is guaranteed to be a parent folder since there are no folders before it. 3. Iterating through the remaining folders. Starting from the second folder, we iterate through the sorted list. For each folder, we check if it is a subfolder of the last folder added to the result list. We do this using the starts with method, appending a / to the parent folder to ensure that only strict subfolder relationships are considered. For example, /a//b starts with I and is thus a subfolder, whereas /a does not start with I and should be retained as a distinct folder. For appending non-subfolders, if the current folder is not a subfolder, it is added to the result list. This ensures that only top-level folders are retained. 5. Returning the result. After processing all folders, the result list contains only parent folders, with all subfolders removed. The algorithm is efficient with a time complexity of O(n*log n) due to the sorting step, followed by a single linear pass through the folders. This makes it suitable for larger input sizes within the constraints of the problem. The solution is concise, leverages Python's built-in string operations, and handles edge cases such as empty input or no subfolder relationships effectively. This is the Java implementation of LeetCode problem number 1233, remove subfolders from the file system. The solution mirrors the Python logic by first sorting the input array lexicographically and then iterating through it to filter out subfolders. Key differences include the use of Java-specific collections like ArrayList and the explicit type declarations required in Java. The starts with method is used to check if a folder is a subfolder, and the plus operator concatenates strings. The result is returned as a list of strings. To solve this problem, let's start with a simple example. Here, the input is a list of folder paths /a/b/c/d/c/d/e/c/c/f. The first step is to sort the input lexicographically. This ensures that parent folders always appear before their subfolders. After sorting, the folder list remains the same in this case /a/b/c/d/c/d/e/c/c/f. Next, we initialize a result list with the first folder in the sorted list, which is /a. This result list will store the folders that are not subfolders of others as we iterate through the input. Now, we begin iterating through the sorted folder list starting from the second folder. For /a/b, we check if it starts with the last folder in the result list followed by a slash, which in this case is a. Since it does, /a/b is a subfolder of /a and we skip it. Moving on to /c/d, we perform the same check using a and find that /c/d is not a subfolder of /a. So, we add /c/d to the result list, making the result /a/c/d. For /c/d/e, we check if it starts with /c/d/ and confirm that it does, so we skip it as well. Lastly, for /c/f, we check if it starts with /c/d/ and find that it doesn't, so we add /c/f to the result. The final result list is /a/c/d/c/f. Let's look at another example with nested subfolders. Here, the input is /a/b/c/a/b/d. First, we sort the input lexicographically, which doesn't change the order in this case. The sorted list remains /a/b/c/a/b/d. Next, we initialize the result list with the first folder, which is /a. This folder becomes the starting point for identifying parent folders. Now, we iterate through the sorted list starting from the second folder. For /a/b/c, we check if it starts with the last folder in the result list followed by a slash, which is a. Since this condition is true, /a/b/c is identified as a subfolder of /a and is skipped. Similarly, for /a/b/d, we perform the same check with a and confirm that it is also a subfolder of /a, so it is skipped as well. As a result, no additional folders are added to the result list, and the final output remains /a. Finally, let's consider a case where all folders are unique. The input is /x/y/z. After sorting the input lexicographically, the order remains the same /x/y/z. We initialize the result list with the first folder, which is /x. During the iteration, we examine /y to see if it starts with and find that it doesn't. Therefore, /y is added to the result, making it /x/y. Similarly, for /z, we check if it starts with and find that it doesn't. So, /z is added to the result as well. The final result list is /x/y/z, where all folders remain because none are subfolders of another. To analyze the time complexity of our solution, we break it down into 3 key steps. First, sorting the folder list lexicographically. Sorting involves arranging the folder strings in order, and this step takes n*log n operations, where n is the number of folders. Since the comparison of strings during sorting can take up to l time, where l is the average length of the folder names, the overall complexity for sorting becomes n*log n *l. After sorting, we iterate through the folder list. For each folder, we check if it starts with the last folder in the result list plus a /. This starts with operation takes l time per folder, and with n folders, this step adds n*l to the complexity. Finally, appending a folder to the result list is an O1 operation, and since at most n folders are appended, this step contributes n time. These 3 steps together form the basis for the time complexity of the solution. Now, when we combine all the steps, the sorting phase clearly dominates the overall time complexity. Thus, the time complexity of the entire solution is n*log n *l. Shifting our focus to space complexity, the input folder list is sorted in place, meaning no additional space is required for this operation. However, we do need space for the result list. In the worst case, all n folders could be stored in the result list, which requires space proportional to O and *L, as each folder string has an average length of L. Additionally, Python's timsort algorithm, used for sorting, has a worst-case auxiliary space complexity of O, n. Combining these, the space complexity is determined by the larger of these two factors, which is O and *L, as the space for storing the result list dominates. When comparing this approach to a brute force solution, the contrast in efficiency becomes clear. A naive method would involve comparing every folder with every other folder to check for subfolder relationships. This results in O n squared *L time complexity, as there are O n squared pairwise comparisons, and each comparison takes O L time. Our optimized solution significantly improves on this by leveraging sorting and a single pass through the list. By sorting the folders first and then iterating only once, we reduce the time complexity to O n *log n *L, which is a substantial improvement. Furthermore, looking at different scenarios, even in the best case, such as when there are no subfolders, the sorting step still dominates, giving a time complexity of O n *log n *L. This is the case regardless of whether the input is simple or complex. In the average case, the solution continues to benefit from its efficient design. While the iteration step may skip many subfolders, the sorting phase remains the bottleneck. Thus, the overall complexity stays at O n *log n *L. In the worst case, where every folder needs to be added to the result list, the solution still performs efficiently. Since the sorting step dominates the other operations, the time complexity remains O n *log n *L, even in this scenario. This consistency across best, average, and worst cases highlights the robustness of the approach, making it a reliable and scalable solution for removing subfolders from the file system. When tackling this problem, there are several common mistakes to watch out for. First, not sorting the input folder paths can lead to significant issues. Sorting is essential because it organizes paths in a way that makes it clear which folders are parents and which are children. Without sorting, your algorithm might miss valid parent-child relationships, causing incorrect results or inefficiencies. Another mistake is performing an incorrect subfolder check. Some solutions simply look for a substring match, but this approach fails to validate parent-child relationships properly. A parent folder must be followed by a / for the child folder to be valid. For example, without this delimiter, folders like /abc and /abcd might be incorrectly considered as parent and child. Additionally, using brute force methods for large inputs can be problematic. Comparing every folder with every other folder results in O n squared complexity, which is impractical for large datasets. Finally, edge cases like empty paths, duplicate folder paths, or paths that are exact matches are often overlooked. These scenarios can lead to runtime errors or incorrect results if not handled properly. Another common pitfall to avoid is introducing memory overhead by using unnecessarily complex data structures, such as nested lists or maps, when simpler options like sets would suffice. This not only increases space complexity but can also make your code harder to debug and maintain. Now, let's consider some key insights that can help you during interviews. Sorting is a critical pattern that simplifies hierarchical problems, as it groups parent and child paths in sequence, making relationships easier to identify. The optimal solution often involves a greedy approach that processes sorted paths and checks parent-child relationships in O n time. This method balances efficiency and simplicity. When discussing trade-offs, it's important to compare brute force solutions with optimized methods. While brute force has O n squared complexity, the optimized approach combines O n log n for sorting with O n for processing, making it much more scalable. Don't forget to explicitly mention edge cases, such as empty inputs, duplicate paths, or folders with similar prefixes, when explaining your solution. Finally, ensure your code is clean and modular, so you can walk through it step by step during the interview. Writing code that is easy to explain is often more valuable than relying on overly clever tricks. This problem is closely related to other hierarchical and graph-based challenges. For example, LeetCode 2.12, Word Search 2, and LeetCode 2.08, Implement Tree, both involve managing hierarchical relationships, often using a tree structure. LeetCode 200, Number of Islands, explores connected components in grids, which shares conceptual similarities. Now, considering alternative approaches, a tree-based solution can effectively represent the folder hierarchy and prune subfolder paths. This method is efficient for hierarchical problems but comes with higher space complexity due to the tree's structure. A simpler alternative is the set-based approach, where you store parent folders and skip any folder that is already covered. While this is more space efficient, it requires careful validation to avoid false positives. Lastly, the two-pointer technique can be applied after sorting the folder paths. This method compares consecutive paths to determine relationships. It's straightforward to implement, but some candidates may find it less intuitive. Each of these approaches has its trade-offs, so it's important to choose one that balances simplicity, efficiency, and clarity for the given problem requirements. Great job! To wrap up, we solved the problem by leveraging sorting and prefix relationships to remove subfolders efficiently. Remember, simplifying the problem through pre-processing like sorting can save significant computation time. Thanks for watching, and don't forget to like and subscribe for more coding tutorials. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!